you say, Sylvia, that's all well and good. Data flow, mesh programming, I'm all on board for that. Why do I care? I'm a humble researcher, or a great researcher, a proud researcher, looking to iterate as quickly as possible. So this is where we're going to talk about, again, starting at high level of abstraction and going down, and showing how we've managed to co-design our software stack with the hardware we've just explored to provide a quality user experience. So essentially, we have this software stack we like to call CS Torch. At the very top level, we have PyTorch, which is going to be familiar to a lot of machine learning researchers and developers. Very familiar, to me, very comforting. I like PyTorch quite a bit. Sitting immediately under that, we have our CS Torch API, which mirrors the Torch API as closely as possible. It's going to provide drop-in replacements for some elements of PyTorch as necessary, some slight wrappers and extensions, basically to help it play nicely with our software stack and ultimately interface with our hardware. If you're familiar at all with PyTorch, you're able to program on different device types. You can specify, say, I want to operate on CPU, or I want to operate on the nth GPU that's available on this system. We've adopted this CS Torch sort of framework and philosophy so that you can basically treat within your PyTorch code the wafer scale cluster, all these CS2s, as a single logical device within PyTorch. Our goal is to have as seamless a transition from existing PyTorch code into interfacing with the CS2s as possible. And then essentially what happens, PyTorch has this lazy graph tracing framework called Lazy Tensor Core, or LTC, that we are an active contributor of. Essentially, as the model executes, we're going to build the computation graph for that model, tracing it with some lazy evaluation. And we're going to end up with this very nice compute graph that we're going to use in just a moment. We're a heavy user of this Lazy Tensor Core framework, but we're not the only users. It's also going to be driving Google's XLA and TPU devices. This is a pretty powerful system. Descending our layers of abstraction, a few more rungs of the ladder. Once we have this nice Lazy Tensor Core, this native PyTorch supported compute graph, we can take a multi-level intermediate representation compiler and basically translate from that compute graph into a more hardware-focused compiler representation, at which point we're going to feed this into our own custom MLIR stack, which is going to handle all of the cluster optimizations and do that final routing, that scheduling, that communication programming we need for all of those 850,000 cores that we mentioned before. That's sort of what's happening at the very bottom level here. And so then we're only transferring our tensors to the cluster as they're needed for that weight streaming process. We send the initial weights over before the first step, again, to perform this compute trace, making sure everything is optimized and ready to go for the actual training or eval execution. And then once we've processed and compiled all of that, we're ready to go. We can sort of begin our training loop hyper efficiently at this point. Excellent. And so on top of that, right, that's also well and good. Sitting at that very top level, let me go back here, sitting at this top level of the PyTorch and the CS Torch API, that's all you really have to worry about as an end user. Our stack will handle the rest. To make life even easier, if you're dealing with something that isn't super custom, we have essentially a Cerebras model zoo where we've implemented a bunch of model recipes, whole bunch of stuff here, right? It supports decoder-only GPT-style type models, encoder-only BERT-style type models, as well as encoder and encoder-decoder T5 style models, but not just sort of monolithic model families. The model zoo also supports a lot of the building blocks for these models. We have all sorts of different positional encodings. You have rotary embeddings, alibi embeddings, et cetera, activation functions, all sorts of attention and feed forward blocks. We've really tried to break out into as much granularity as possible so that even if you're working with a model that isn't natively supported in our model zoo, like say StarCoder or GPT-3 or Llama or what have you, we can sort of leverage these building blocks to make your model porting experience easier. And we'll touch on model porting more here in a bit. We're also going to provide checkpoint converters to and from the Hugging Face format, as well as across different versions of the Cerebras software stack for most of these models as well. So if you have, say, like a Hugging Face evaluation harness you're using, or you have a pre-trained checkpoint, or you've already done some preliminary work in Hugging Face, you can port that over to CS2 fairly easily, and then translate it back out for your evaluation, or if you're doing deployment or serving, or whatever needs you have on that front. And again, as a reminder, as long as you have a sufficiently large memory X module, you can run even the biggest models on a single CS2. For instance, Llama 70B is going to require over 1 terabyte of memory for the weights and optimizer states, but you can pretty feasibly run fine-tuning of that 70 billion parameter model on a single CS2. Obviously, if you're doing a lot of continuous pre-training or training from scratch, you probably want more compute, but you can do quite a bit of work without a ton of CS2s as well. Perfect. So in terms of what it actually looks like to start programming and training on a CS2 cluster, relatively simple, right? We're going to define our model in PyTorch, whether that be using, say, an existing model zoo representation, or we're implementing it ourselves with those CS-torch little drop-ins we need to make things play nice. We're going to parameterize the model with a standard YAML config template. And then we're going to write, again, treating our model like we're writing it for a single device. All the translation and distribution is going to happen on the Cerebras software stack. You don't have to worry about any of that. As an example, we have this GPT-3 XL, a snippet of a YAML file on the right. We're just defining hidden size, how many hidden layers we have, etc. And then to actually train it, each model family in the Cerebras model zoo has a run.py function. It can also act as a template for your own model family. And it provides these common set of arguments. We basically just need to point to what's the run.py is defining essentially the family of model we're using. We point to the model YAML config. We specify how many CS2s or CS3s, hence the CSX. The number of devices we're using, how long we want to train it for, where we're saving our checkpoints, whether we're doing train or eval. And then we can just kind of go. Then your job will get enqueued to the system and execute from there. Overall, quite straightforward, if I do say so myself. So if you want to scale up to a larger model, that's no biggie, right? Because we've already defined the entire model family. We just have to go into that YAML from before. And if we want to go from, again, GPT-3 XL, which is about 1.3 billion parameters, we just want to take that up to 20 billion. We just have to upscale our hidden size, number of hidden layers, number of heads. If we're trying to match a model scale from a paper, that's usually all pretty readily available information, unless it's something like a GPT-4. And if we need more compute to make that work, we're just going to upscale the number of CS2s that we're leveraging in our run.py commands. And again, just execute, it will just work. It'll just scale up. No other real changes we have to make on the user end. So yes, just really emphasizing here, we can really scale up to arbitrary numbers of CS2s in our cluster with a one-line change. This enables what Natalia said before, where we can conduct a lot of initial experiments, a lot of small-scale ablations on tiny versions of the model. And then you can really upscale the sort of most fruitful experiments from there with no change to the overall workflow. It makes experiment tracking quite straightforward. We don't have these like grossly just disproportionate implementations of the model that go from sort of small scale prototype to all the ML engineering we traditionally have to do on GPUs to upscale, say, to hundreds of devices. In this case, all the same code, very clean, easy to track, no multiple implementations that can introduce error or consistency in scale out. Perfect. Quick water here. So when we talk about this reduction of complexity using CS2s, there's this really good, we were inspired by Andrej Karpathy and his nano GPT implementation, which is essentially like a 100 or so million parameter model, very small. It's implemented in this very simple code base that's meant to be a sort of educational tool that you can use to wrap your head around LLMs and LLM training pretty easily. We had a teammate who was inspired by that, essentially converted that premise into our software stack. And using a similarly sized code base, around 1,200 lines or so, you can execute similarly simple model, anything between 20 billion and 500 billion parameters. For reference, as we start to scale up in a more traditional GPU setup, we're going anywhere from 24,000 lines of code all the way up to 62,000 lines of code if we're doing like a really large deep speed experiment over 1,000 GPUs to handle a model of that size. Again, same code base on CS2 across all of those, no real ML engineering overhead added. Really crucial for having fast iteration, fast experimentation, clean code. We're all about that. Getting to market, or if you're a researcher, to publication, to innovation, much faster with larger, more accurate models. And we talked before about the sort of efficient scaling. This is an example of that. We have experiments across all sorts of size models, going from 1 to 16 CS2s. And basically, if we just project outwards, and we've seen since this graph was made, I believe, that linear scaling is preserved as we increase up beyond 16 CS2s. You're going to get the scaling you expect, regardless of the model scale, which is very convenient when we're doing our large scale experiment planning, budget estimates, timing estimates, all of that. There's no sort of weird drop off curve because, again, highly efficient scalability, ease of communication. Data parallelism is a very conceptually straightforward paradigm that's going to scale consistently as it grows.